Hey, welcome to Physics 1403, Stars and Galaxies. We're going to continue our discussion of stars this week. And our last video, we talked about what was a star, what powers a star, but we really didn't talk about where they come from. And in order to do that, that's what the purpose of this video is. We're going to talk about the birth of a star. Reminder, a star is a sphere of gas held together by its own gravity. It is self-luminous black body that shines by radiation derived from an internal energy source, specifically nuclear fusion. And in our last video, we talked about the proton-proton chain as one of those internal uh, energy sources. All right, so where do stars come from? Well, first of all, stars don't start off as stars. They actually start off as nebulae. All right, and there's a couple different kinds of nebulae that interest astronomers. The first one is an emissions nebula, and emissions nebula are usually very big, and they are filled with hydrogen. And what happens is that they are near a bunch of large stars, and those stars, the radiation coming off of those stars, excites the energy of the nebula, and so they begin to glow, and that's why we call them an emissions nebula. These guys are very warm because of all that energy. That's actually, if you've ever seen something so hot that it glows, if you've ever watched a show about blacksmithing or something like this, where they put that sword in the forge, it pulls out and it's glowing hot. That's what we're talking about when we talk about an emissions nebula. They're very warm and they're not very dense. All right, there's not a lot of particles, not a lot of atoms floating around in an emissions nebula, but there is enough that they will begin to glow. They can give birth to stars, but they're not the usual source. Another kind of nebula is called a reflection nebula. And a reflection nebula is actually not a nebula, it's really more like a gas cloud that there are really bright stars behind it. And so as the light of those stars comes through, they kind of get diffused out and they begin to glow. A good example of this is if you have a good telescope and you look at the Pleiades, the Seven Sisters, right? They tend to have kind of a halo around them. That's an example of a reflection nebula. By the way, the Crab Nebula is a good example of an emissions nebula. We're mostly interested for stellar fusion or starbirth. We're mostly interested in dark nebula. And by the way, if I was ever going to start a rock band, I would absolutely use the name Dark Nebula as a rock band. A bunch of astronomy nerds making music, you know. So anyway, so a dark nebula is number one, they're very dense. And they're not just hydrogen and helium. Oftentimes it'll be carbon monoxide, which is carbon and oxygen together. And so they got a lot of enriched materials there. And so they have that 75% hydrogen, 24% helium, and that 1% other stuff. And in fact, that's that other stuff that we usually find them with is because we find the carbon monoxide signatures on the spectroscopy. All right, they are dense enough that they block light behind them, which is why they're called dark nebula. Horsehead Nebula is a good example of this. And so we find them not just by the infrared that they give off, but also because they form blank spots in space and like all these stars, and then there's a little area there where there's no stars. Anyway, by comparison to other nebula, they're really very dense. They have a lot of materials, and their materials are very cold. And that's kind of important because that means that if something were to come along and disturb this nebula, say the explosion of a nearby supernova, that would disturb this dark nebula. Or maybe two gas clouds running into each other, that would also disturb this nebula. Or maybe if you ever look at a picture of the Milky Way, which we will do in class one day, you'll notice that we have these spiral stars, and these spiral stars look like they're glowing blue. That's because as everything spins around, it's moving at different rates relative to each other. And so gas clouds along those front arms are packing into each other. And what all three of those things do is they create areas where the nebula is not evenly distributed. In other words, there's an area that maybe has more mass than the rest of it. Now, they're already heavy. Some of them can already be like 100 to 1,000 solar masses, right? And they're huge, light years across, right? But you start packing this material in kind of a little bit smaller space. Now you have a place where gravity can begin to take over. Remember, gravity is directly related to mass. And so if you have an area where that's more massive, then materials are going to be drawn to that area. And because the nebula is, at least at this point, cold compared to like an emission nebula or something like this, there's not a lot of energy bouncing them off of each other yet. So they begin to pack together. And as they begin to pack together, the amount of energy will begin to go up. Okay? I don't know how many of you have ever made a snowball. I mean, I'm in West Texas. We don't get a lot of snow where I'm at here, right? But if you've ever had a snowball and you have to pack it together, and if you have to push it down a little bit in order for it to pack, in order for it to keep its shape. All right, well, what you're really doing during that time period is you're applying pressure, and that pressure raises the temperature inside of that snowball. And then when you release it, that snowball refreezes into a more solid mass. All right. So what, in other words, I guess what I'm saying is that, and by the way, there's a chemistry law called Gay-Lussac's law that describes this: the higher the pressure, the higher the temperature. So when you take a gas like helium and hydrogen, and helium and hydrogen, and you pack it together, temperature is going to begin to rise. When it gets to be about 2 or 3,000 Kelvin, okay, the Kelvin system is very similar to the Celsius system, just a little off on one number, on the about 273 off of where it was. So you could just substitute Celsius in here and you'd probably be just fine for the most part. So when it starts reaching about 2 or 3,000 Kelvin, there's enough heat there that mass is going to begin to glow. In fact, if you were to take something like say a star like our sun that was one solar mass, all right, it would begin to glow at this temperature, but it would still be really, really big, all right, like around 20 times the radius of our sun, all right, because it's not densely packed in there, but it is packed in there enough that it's beginning to heat up. And you might say, well, yeah, well, what about that emission spectrum? Because it's already starting hot. Yeah, but it's almost, in some ways, it's like it's too hot to start the packing material, if that makes sense. Although when you start stacking emission spectra on top of each other, like you see along the front edge of these spiral arms, exact same thing can happen. All right, so now you have what we call a protostar. It is beginning to glow, but that glow is not coming from nuclear fusion. That's why it's not a star yet. It's a protostar. And this is just from heating up the gases. We have the exact same thing happen, like for example, during shooting stars. What you see when you see a shooting star is the air in front of that bit of extraterrestrial material is pushed together by that grain of sand or that piece of ice or whatever it is that we're passing through, right? And it's being packed together and it's being superheated into a plasma that's glowing. That's what we see as a shooting star. So think something like that, but way, way bigger. So again, our sun probably would have been about 20 times the radius of its current self, right? And probably 100 times brighter than its current self. Okay? And the reason, or more luminous, I should say, not brighter, more luminous. Remember, luminosity is the amount of energy that it gives off every second. Brightness is kind of a relative term. How bright something is, like this is bright because it's close to us versus it's bright because it's very luminous. So that's, brightness is a little relative. Luminosity is an actual number. Right? So it may be 100 times more luminous, 20 times the radius, but only about 3,000 degrees. Right, but it is going to begin to glow. Energy from that heat is going to be giving off. So now we'll be able to see it. And if you look at places like, for example, the Pillars of Creation, which is a really wonderful picture from NASA that I'm pretty sure I included in a little fact sheet that I put together about this on the birth of stars. You can see oftentimes you'll have multiple protostars in a region. Again, these nebulae may be huge. They may be, hundreds of light years across. And because they are so large, you can have what we're experiencing this with these protostars can actually happen in multiple places. All right. And in fact, probably a third of the systems in the Milky Way are actually binary systems that have two stars. So that are orbiting each other, usually one large star and one small star. So they're doing this. But either way, Alpha Centauri is a three-star system. So the stellar nurseries gave birth to three stars at about the same time. So anyway, so going back to my protostar, it's glowing, it's getting bigger. Of course, the more mass it pulls in, the heavier it becomes. And of course, the heavier it becomes, the more gravity it has, the more mass it begins to pull in. So what we have here is this almost this runaway positive feedback system that's going on here, right? Until eventually the internal temperature of this protostar is going to be hot enough that it's going to ionize the hydrogen. Remember from the last video, if you haven't watched it, The Birth of Stars, watch that one first. The hydrogen, once it's been ionized, it's now a naked proton, basically. And then the temperature is going to continue to get hotter and hotter and hotter until eventually at about 1,000,000 Kelvin, those hydrogen, those naked ionized, or these ionized hydrogens are going to slam into each other, and that's going to begin the process of fusion. And this is going to be an important point in the star's life. Right? Because number one, it is no longer a protostar, it is now an official star. Remember, internal energy source, specifically nuclear fusion. Now it is officially a star. It's also no longer going to be pulling in material. Okay? So when the star, so at the same time that it's gathering up all this material, right, and you have that protostar developing and temperature developing, oftentimes you have a lot of other material that is, we call a planetary disk or an accretion disk. And that accretion disk is full of dust and it's full of ices, maybe atoms of metal, all these different things like this, right? And they are orbiting around this sun because of something we call angular momentum. Okay. And so, but what happens is once nuclear fusion begins, so I guess what I'm saying is that you have the sun, but you still have all this dust around it here. Okay? Once nuclear fusion begins, you have this burst out, almost an explosive burst of what we call the solar wind, a bunch of ions. And it is so energetic that it clears that planetary accretion disk out away from the protostar. And so from that point on, it is no longer collecting new mass. It is no longer collecting new material. And instead, it pushes it out. And that material, in this case, like in the case of our solar system, that was about, I don't know, maybe 1 or 2% of the mass of the sun was actually blasted out and to become, I guess 90% of our mass of our solar system is our sun, and the other 10% of that disk became all the planets, asteroids, comets, leftovers, vagabonds of the solar system, things like that, that are orbiting our sun. And there was a lot more of them once upon a time, but that's another discussion. Okay. So that means that the star is no longer getting mass. And if you watch the other video, you know that mass, I drew some pictures over here, mass determines the internal structure of that star. Mass also determines how long that star will last before it dies, because the more massive it is, the hotter it is, the faster it burns through the fuel that it has. Which is why a red dwarf, though relatively small, will last a lot longer than a supergiant blue star like Rigel or Vega. Anyway, so at that point, a star is a star. Again, it started off as a big cloud of dust. It started off as and this dust may float around for billions of years until something comes in and disturbs it. Something comes in and causes regions within that nebula to be more dense, have more mass than others, and then gravity takes over. All right, and that gravity, the mass, the energy, everything from that is kind of foreordained. It's just going to happen. This whole process, by the way, from the actual disturbance until the birth of the star, this could be 20,000 years. And I think it's probably reasonable to ask this question because the life cycle of a star is so long. No human being has ever observed the life cycle of a single star. And we live, what, 80 years, something like that, compared to our sun that's 4.5 billion years and has another 5.5 billion years to go. We've got, so I think it's reasonable to ask, how do we put all this stuff together? And I'll go ahead and answer that question. While we may not be able to observe the life cycle of a single star from nebula to protostar to star to everything that comes after that, all right? Instead, though, we can observe these phases on different stars, different protostars. Again, I mentioned the stellar nursery, the pillars of creation, that you look at that and you can see stars at different phases of their development. And so then you can put it together. Oh, okay, so this is what's going on here. And then I look over here. This is a star that is a protostar that is very luminous, very large, but thanks to Wien's law, we can look at it and go, not very hot. And so there's not going to be fusion going on because we know what temperature fusion happens. That's something that has been tested in a lab. And so we look, instead of at a single star, we look at stars that are in various places in their birth. And from there, then we're able to piece together a little at a time what's going on with birth. We're going to do the same. We're going to have the same thing when we look at the life cycle of stars. That what happens to a star that's a medium-sized star that leaves what we call the main sequence. We'll talk about it in class. And what happens after that? Where did white dwarfs come from? We did that by researching it and looking at it and then piecing it together. So while it is true we have never seen this process that I just described laid out by watching a single star, we have seen the entire process by observing hundreds and thousands of stars and then piecing them all together. And so I think that's for me that's fine. All right, so that kind of concludes this video, and in class we're going to talk about these stars because they are different masses. In class we're going to talk about what those mean and a really super useful tool called the Hertzsprung-Russell diagram, and we'll make our own, and we're going to see if we can't see some patterns as a result of that. All right, until then, I'll see you in class.